So slope fields go right along with differential equations. They go hand in hand. Kind of like, you know, when you have y equals x squared and you draw the graph and it's a parabola, slope field is a visual representation of a differential equation. So it is a representation of infinite solutions, which is actually just super cool. And I mean, I realize I'm a math nerd, but you guys, you're in BC Calc, so you are too, all right? It's cool. It's an infinite number of graphs on one grid. That's neat. That's so cool that you can graph an infinite number of graphs on one grid. So that's cool. Spoiler alert, they're a little bit tedious to do, to like draw them, but you'll be okay. All right, if your differential equation only has x's in it, like there's no y's, all your columns are the same, which means you can knock out whole columns at once, which is nice. You don't have to go point by point tediously. And if you only have y in your differential equation, all the rows are the same. And you can think of that like, you know how y equals is a horizontal line and x equals is a vertical line, like that. So we're going to do a lot of things for each one of these, and that's because I want you to make connections between the slope field, the differential equation, the general solutions, and the specific solutions. We're gonna do all these things for each one of these, so you can kind of like put it all together. We're going to draw the slope field, describe what the solution, almost said situation, describe what the situation looks like. So just describe the graph, solve the differential equation for the general solution, then for the specific solution, I'm going to give you an initial condition, and then we'll draw that specific one, the particular solution in on the slope field. All right, so looking at this first one, do you see how there's only an x, there's no y? That means we can knock out whole columns at once. So let's start with the first column. What is the x value for every single point in this column? -2, 2, -2, 1, -2, 0, they're all -2. That's why you can knock out the whole column at once. If you plug -2 in for x, what do you get from this differential equation? If you plug in -2, 3, it's a representation of slope. You want the slope to be 3 at each one of these. Now, if you're a very type A person, this is going to kind of bother you because it's not going to be perfect. It's going to be like, good enough. You want to draw a little line segment with a slope of 3 for each of these. It's not an exact science, and you're not really going to be able to see where I'm headed until I get the whole picture drawn. So just kind of bear with me for a minute. The slopes don't need to be perfect. They just need to make sense in relation to each other. Once you get the whole picture, it'll make sense, or you'll at least be able to see the whole thing. All right, what is the x value for every point in this column? -1, perfect. If you plug -1 in for x, what do you get? 2. The slope, remember dy dx means slope, should be 2 for each one of these. Now, if this was 3, 2 just needs to be like less steep than that. Again, just in relation to each other, they need to make sense. So do you see how I made them a little bit less steep? Like we had 3 and then we had 2. What is the x value for every point in the next column? 0. If you plug in 0, you're going to get 1. So these should all have a slope of 1. So again, a little bit less steep. For the next column, x is 1. If you plug in 1, what do you get? 0. And those are the easiest ones to do because those are going to be horizontal line segments. And then the last column, x is 2. If you plug in 2, what do you get? -1. So it should look just like this positive one, except going down. And that is your slope field. It's a representation of an infinite number of solutions. Let's describe them. If you were to draw in solutions, like you would start here and kind of flow with the slopes, what shapes are you getting? Like, what would this look like if I drew in solutions? They'd be parabolas that are upside down. I'm going to call that reflected. You can write upside down, doesn't really matter, but reflected parabolas. Yeah, isn't that cool? It's neat. You can disagree, but Jenna and I are right. Now, the reason it's an infinite number of solutions is, look, you could have one here, or you could have one up here, or you could have one up here, or you could have one up here. Like it's an infinite number of parabolas at once. That's so neat. All right, now we're going to solve the differential equation. You would multiply over the dx. This is what we were just practicing at the board. So if you were like, hey, I didn't quite get that, well, we're going to do a whole bunch more practice. Or I don't know how many examples. I only have 5 on here, so not that many. All right, then your antiderivative. So we're going to have y equals x minus 1/2 x squared plus c. You can leave it like that, but I know a lot of people like to have the square term, like, you know, you like to have it go in descending order. So I'm going to rearrange it if you feel like it. If not, that's fine. Negative 1/2 x squared plus x plus c. Is that an equation of a reflected parabola? Why? It is, but why? Negative and the x squared. All right, so it makes sense. Do you see the connection there? You want to make sure that those kind of like match. All right. Now let's write for a specific one. This is an infinite number of answers. Now let's do one specific one. We're going to plug in 0 for x, 1 for y. If we plug in 0 for x and 1 for y, what is our c value going to be? 1. Perfect. And so your equation would be y equals negative 1/2 x squared plus x plus 1. Yeah, I think that's, yeah, it's one side, it's like echoing around here. So this is an infinite number of solutions. This is a representation of an infinite number of solutions. This is one solution. Okay, just wanted you to see the difference. All right, and then the last thing we're going to do is draw that in on the slope field. We're going to draw this specific solution onto the slope field. Here's what you do. You start at the initial condition, which is 0, 1. So you're going to start right here, 0, 1. And what you do is just kind of like flow with the slopes, all right? You shouldn't run into any of the other slopes. You just sort of use them as guide arrows. I guess you would run into one if that specific point was also on the graph, but you just want to kind of like use them as a guide. It's gonna like do something like that. See how I'm not actually hitting any of them? You just kind of go in between. Someone once said it's like you swim with the fishes, but that means that you're dead. So I don't know, like, but anyway. Now they do put these on the AP exam and it's kind of cool. They make it worth a point to draw that in. It's like the easiest point in the world to get. You just draw that in. It's also easy to mess up. They won't give it to you if you don't go all the way to the edge. Like for example, if I drew this and stopped here and didn't go all the way to the edge of the paper, they will not give you the point. Okay, so just make sure you draw it like all the way to the edge. I mean, it's not an exact science, really. I mean, it would be like, is it really off? Like, how far off is it? Like, if you made this go over here or kind of run into that one, fine. But like, if you made it go all the way over here, then they would probably not. I think it's like, how wrong is it? Okay. All right, let's try another one. Do you see how this only has a y in it? We're going to knock out whole rows at once, right? What is the y value for this entire first row? 2. If you plug in 2 for y, what do you get for your slope? 1. 2 over 2 is 1. So we're going to have a slope of 1 for all of these. Again, it's not perfect. It's like good enough. All right, for this whole row, y is 1. If you plug in 1, you get a half. So if this was 1, a half just needs to be like less steep than that, which actually, let me go back and make my 1 a little bit steeper. Sometimes you need to do that, like in relation to each other, they just need to make sense. So I need my 1 to be steeper than my 1/2. Again, it's not perfect, and I'm not here to grade your art skills. Like, just do your best. All right, for all of these, you're plugging in 0 for y. That's going to give you 0. I kind of bolded those ones since it's on the axis so you can see it a little bit better. And then down here, isn't it all the exact same stuff except negative? You can just take these and reflect them over. It's really nice when you can do that because it like simplifies things. Like you can just do half of it and then take those and reflect them to the other side. So let's describe what they look like. If you were to draw in solutions here, what kind of graph did you end up with? Like if I were to draw in a solution here. Yeah, good, it's exponential, perfect. Now the important part is the horizontal asymptote. So let's say that we have a horizontal asymptote at y equals 0. Now remember, you're looking at an infinite number of solutions. So you could have one here or here or here or here or here or here. So it's an infinite number of answers. Isn't that cool? That's cool. It is. All right, so when we solve this, we should get an exponential. Like it should make sense. If you get two things that don't match up together, then like you had a whoopsie, all right? So we're going to divide over the y. It'll be 1 over y dy equals 1/2 dx. The 2 is still on the right side, but it's in the denominator, so 1/2. And then antiderivative. So what do we get on the left? ln, perfect. And then over here, 1/2 x plus c. And then we want to get y by itself. So you're going to exponentiate. So it's going to be y equals, good, c e to the power. No, I'm glad you were like excited about it. Fx, good. The plus minus comes from the absolute value. Again, remember me running back and forth across the room. And again, that's because you could have an answer up here or you could have an answer down here. It's an infinite number of answers. Whenever I give this test, because I give the same test, we're still doing Calc A-B material. I take off almost every single person's paper for not putting the plus minus. And it's not me being picky. It's super important because there's an infinite number of answers. Like that's a really huge thing that you have to understand. I keep saying it over and over, so I think you guys have got it. Anyway, make sure you put that. Now for the specific one, we won't put that because we're getting one specific answer. So we're gonna go back to this step before we did any solving. We're going to plug in 2 for x, -1 for y. Now, when you put in the -1, you absolute value it, so it's +1. ln of 1 is 0. And then if you plug in 2 for x, you would get 1 plus c. So c is -1. And so I'm going to recopy this line, but I'm going to put -1 in for c. Again, I kept covering that up because you want to do that work before you do any solving. Now we're going to solve for y. So it's going to be e to the power of. And I did put a negative out front. Why did I do that? Your initial condition is negative. So we're going to have an answer that's a solution that's down here. So all you have to do is start at the initial condition and then swim with the fishes. Like just use those slopes as guidelines, right? So we're starting at 2, -1. So that's right here. So start at 2, -1. And it's just going to do something like this. It's going off the paper. So this one isn't like super interesting, but that's all it is, just a swoop. We're doing okay on time, so we'll do one more and then I'll give you a break, okay? Unfortunately, this next one has both an x and a y. That means you have to go point by point, okay? However, do you see how there's just an x in the denominator? On this side, all the x's are positive, and on this side, all the x's are negative. So we can do just this side and then reflect it over. So like, yeah, you have to go point by point, but it's not going to be too bad. Also, you can knock out whole rows and columns where it will be 0. What's going to make the numerator 0? So everywhere that y is -1, you will have a 0 slope. So right here for all of these, y is -1. So you would have a 0 slope for every single one of those. So you can knock out that whole row. And then if x is 0, you would have a 0 denominator. If you have a 0 denominator, it's not horizontal, it would be vertical. Yeah, undefined. So you can put an undefined slope for all of those. You know, except for the one where they're both 0. I'm going to have to erase here. I should have done that one first. If they're both 0, you have 0 over 0, which is indeterminate, and you would leave that dot blank. You can't put anything on indeterminate. So what would that be when x is 0 and y is -1? So this one right here. So that one needs to stay blank. This is a Miss Cole thing, not in anybody else thing. So if you like look in a book or the internet, you won't see this. But here's what I usually do for those. Because it's supposed to be blank, I usually bold the point, because if I leave it blank, I'm going to think I forgot to do it. Whereas if I bold it, then I'm like, oh, I did that. It's just there's not supposed to be anything there. So that's what I do. You don't have to do that. That's just like my suggestion. All right, so let's do this side where all the x's are positive, and then we'll just reflect them over. All right, so this point is 1, 2. You plug 1 in for x, you just have 1 there. If you plug 2 in for y, what are you going to have? 3. All right, 3 over 1, which would be 3. So I don't know, something like that. This is the point 1, 1. If you plug 1 in for both of them, you're going to get 2. So just make it like a little bit less steep. This is the point 1, 0. That would give you 1 over 1, which is 1. So a little bit less steep than that. And then this one is 1, -2. Let's see, -2, that would be -1, right? So like that. All right, this is the point 2, 2. Oh gosh, what is that going to be? 3 over 2. 3 halves would be 1.5. All right, this one's 1 and this one's 2. So like something in between that. Good enough. Like it's not going to be perfect. This one is 2, 1. That would give you 2 over 2, which would be 1. This one's 2, 0. That would be a half. So the least steep that we've seen so far. And then this one is 2, -2. That would give you -1/2. Again, they just have to make sense in relation to each other. Now take all of those and flip them for the other side. Flip them like a pancake. It's really tedious when you can't knock out whole columns and whole rows at the same time. But look, we lived. And doesn't it look cool? It looks like a firework or something. Like a sea urchin. Oh, like a pufferfish. Now this one's hard to describe without working it out. So we'll work it out first and then describe it. I like that though, a pufferfish. Sea urchin. All right, so we are going to divide over the y plus 1. You have to keep that together. You can't separate the y from the 1. So we're going to divide over the y plus 1, multiply over the dx. And the x is still in the denominator. So it's a 1 over x dx. So the left side is going to be ln y plus 1. Because the y is in the numerator. That's why. So you have to divide that over. Now, technically, there would be a u substitution there, but derivative of y would just be 1, and then plus 1 is a constant, so there's nothing to see. It's like nothing to see here. And then this side will be ln of x plus c. All right, then to cancel out ln, you're going to do e to the power of, exponentiate both sides. This is going to give you y plus 1 equals, and then over here you're going to have plus and minus to get rid of the absolute value. E is a number, c is a number, so it'll just be a constant. And then the e and ln cancel, so it's just absolute value of x. Hey, Ms. Cole, why do we keep the absolute value there? You have to keep it on the left side. Putting the plus and minus gets rid of it over here, but you need to keep it on the right side. There's no way to get rid of that. And then your last step would be subtract 1. So description, what are they? Well, what kind of function is this? Absolute value. It's going to be a V shape with a sharp point Where? Look at the slope field. Perfect. Not differentiable due to sharp edge. That's why that happened there in the slope field, is because that's where the point of the V is going to be. Hey, Miss Cole, didn't you say it was an infinite number of graphs? Yes, but they would all have their point there. Watch, I'll point to it. You could have a really steep one like this. You could have one like this. It could be reflected, but no matter what, the point is going to be right there. Does that make sense? Okay. Now let's do the initial conditions. So go back to this step right here. We're going to plug in -2 for X, 0 for Y. All right, if you put in 0 for Y, you get ln of 1, which is 0. Do you notice how that always happens? I choose it to be that way because otherwise you would need a calculator. All right, equals. Now, if you plug in -2 for X, you would absolutely value that. It would be +2. So you get ln of 2 plus C. And so what is C going to be? Yeah, you have to subtract that over. So negative ln of 2. So we're going to recopy this line. And again, I keep covering this up because you want to work with it before you do any solving. So recopy that line, except put in the negative ln of 2. Every single term has an ln in it. Don't worry, they're all going to cancel. We're about ready to cancel them all out because we're going to exponentiate. So it's e to the power of all of this. We get y plus 1 equals e's and ln's cancel. Do you remember how we talked about when you multiply, you add your exponents? When you divide, you subtract your exponents. So since these are being subtracted, we're going to divide. It's going to be absolute value of x divided by 2. Again, those are your exponent rules. Let me write one on the board. Make up a number for me. And another one. All right, when you multiply, you would add. This would be x to the plus. When you divide, you subtract. So since those were being subtracted, it was a division problem. And then your last step is subtract the 1. And so when we go to graph that, it's an absolute value graph moved down 1. This is the point. And think of this as a 1/2. You would go up 1 over 2 for each side. Now it is going to actually hit the slopes because each side of the absolute value is linear, so it's going to go through them exactly. And that's your one particular solution. Number 4. We're going to have to go through point by point for this. Here, you know what? All right, so these are hyperbolas. Centered at this. What is that? -1, 0. So for this one, we would cross multiply. It would be 2y dy equals x plus 1 dx. So antiderivative, the left side would be y squared. The right side would be 1/2 x squared plus x plus c. And then to get y by itself, you would square root. Now for the general solution, you would have to put plus and minus. And that's what causes it to look like that. Like you have a plus and a minus. Square root of all of this. Now for the particular solution, I'm going to go back to this step. I'm not going to cover it up because I know some of you are still writing it, but I'm going back to this step, the y squared equals blah, blah, blah. We're going to plug in -1 for x and 1 for y. That would give us 1 equals, what would that be? 1/2 minus 1 plus c. It would be 1.5. And so you're going to have y equals square root 1/2 x squared plus x plus 1.5. Why did I do a positive square root? Oh, and then drawing it in. you would start at -1, 1, which is right here, and then just flow along with the slopes. Like you don't want to run into any of them, but just like use them as a guide.